This is lecture 10 on urban transportation planning. In this lecture, we will continue our discussion on trip generation analysis. You may recall in the previous lecture we started our discussion on trip generation analysis. We defined a trip as a one-way movement from an origin to a destination. We also made a particular point very clear in connection with trip. As far as origins of trips are concerned, we consider zone centroids as trip origins. Destinations are also zone centroids. So it is just a movement between zone centroids. Then we try to differentiate between trip production and trip attraction. Trips generated at residential zones are termed as trip productions, and trips generated at non-residential zones are trip attractions. Then we further classified the trips into home based and non-home based trips. Can anyone define home based trips?
One trip ends household. Home based trip.
A trip having at least one end at a household is a home based trip. Then obviously non-home based trips will have neither of its ends at home. The ends will be connected to non-home activity centers. Then we classified the home based trips into different types, starting from work trip, educational trip, social recreational trip, shopping trips, personal business and work related business trips. Then in the process of a discussion on trip production modeling, we try to identify the set of variables or factors that might influence trip production. What are the factors that might influence trip production? Of course, the factors are related to household characteristics, isn't it? Can anyone list the factors influencing trip production? Yes, please. Any volunteers? No? I think you have to recollect faster. We started identifying the factors starting from the size and composition of household, then number of workers in a household, number of students in a household, household vehicle ownership, household income and so on. Then we were just discussing about an analytical technique which will be suitable for this kind of analysis, trip production analysis, which basically involves relating a dependent variable with a set of independent variables. And for this purpose, regression analysis is found to be more suitable compared to other analytical techniques. To understand the basics of regression analysis, we took up a simple example involving one independent variable and try to understand the basic analytical procedure in the regression analysis, and then we also listed some of the important results related to regression analysis. And the results that we have seen are this. We just assumed a very simple linear regression equation as ye to be equal to a plus bx. Now we are clear that we can estimate the regression coefficient b to be sigma xy by sigma x square, and the intercept constant a is given as y bar minus bx bar, and of course we define lowercase x small x as x minus x bar, y as y minus y bar, and x bar and y bar are nothing but the means of the x and y observations respectively, the observed values of x. Right? Please note here we indicate the actual observed values with uppercase letters, and the x1, y used for your analysis are lowercase letters, the difference between the observed value and the corresponding mean. Then we discussed about the sums of squares. We identified 3 different sums of squares, and we also looked at this particular relationship as sigma y squared to be equal to sigma yd squared plus sigma ye square. It is better to understand the description of each of these sums of squares. Sigma y squared is nothing but the total sum of squares of the deviations of y observations about the mean value. It is nothing but y minus y bar square summed over all the observations, is not it? That is what is meant by this particular statement. And sigma yd squared, as we have seen with the help of a figure, is sum of squares of deviations of the y observations from the regression line. We just measure the deviation up and down from the regression line of the observed values and get the value of yd and then sigma yd squared. Then sigma ye squared is the sum of squares of the deviations of the estimated value of y, which is ye, about the mean value, which is also termed as regression sum of squares. We find the difference between ye and y bar, square it and then sum up to get the value of sigma ye squared. And to go further on this particular sum of squares, we need to understand that the residual sum of squares sigma yd squared provides a measure of variability of y observations about the regression value, is not it? And sigma yd squared, if you find the value to be small, then the regression equation may be considered to fit the observed data well. And we also discussed about this particular coefficient, the ratio of the sum of squares explained by the regression to the total sum of squares is known as the coefficient of determination, which gives an idea about the level of utilization of the regression equation or level of effectiveness of the regression equation, and is usually denoted by the symbol R squared, or we can give the value of R squared to be sigma ye squared divided by sigma y squared. You know now what we really mean by sigma ye squared and sigma y squared. Let me throw a little more light on the concept of R squared, so that you are able to appreciate the significance and importance of this particular coefficient. Additional explanation about R squared. Let us try to understand the concept with a simple data set involving just 5 observed points of x and y. That is what I have done here. I have just made a scatter diagram pertaining to 5 points, is not it? And let us say this is the regression line which fits the 5 points reasonably well. Then let us say this is the mean value of the y observations, say y bar. Obviously it is a constant, so the line is going to be a horizontal line. And let us say the coordinates of point 1 are x1 and y1, and point 2 x2 and y2, point 3 and so on, say point 4 x4 and y4. So we need to identify here the values of y, ye and yd. If we can pictorially perceive things, it will remain in your memory much better. So, let us try to identify those values. Obviously, ye4 is as shown here. This is the estimate of y4. Estimate of y4 is shown here as ye4, is not it? And this is the deviation from the mean, and we name it as ye, and this is how we should understand y, deviation of observed value of y from its mean. And we are trying to calculate r squared using the values of ye and y, is not it? So, we can write now r squared to be equal to sigma ye squared divided by sigma y squared. You can understand how we calculate the sums of squares of the deviations and get the value of r squared. Clear? Now, what is the maximum possible value of r squared? You have the picture in front of you and you have the equation. Can anyone tell me what is the maximum possible value for r squared? Yes, 1. Perfect. If there is no deviation at all between the observed and regressed values, obviously the denominator and numerator are going to be same, is not it? So, the maximum possible value is 1. What is the least possible value? If the independent variable is not explaining the dependent variable at all, 0 can be 0, right. So, that is the range of values for r squared. Of course, for completion's sake I will show you the value of the other deviation also. So, this is how we need to understand the deviation with respect to the regression line as well as with respect to the mean. Is that clear? Okay. So, the ratio r squared may assume a magnitude between 0 and 1. For a regression for which r squared is equal to 1, there would be no variation remaining that is unexplained by the independent variable used in the regression equation. That means your independent variable is so effective that it is able to explain the whole of the variation of the dependent variable, right. And will it happen in practice? It is very rare, it may not happen, it is only an ideal situation which can be understood theoretically. And when r squared is equal to 0, the independent variable used would not explain any of the observed variation in the dependent variable. There is no relationship at all between your independent variable and the dependent variable, right. So, that is how you must understand the significance of this particular coefficient. It exactly gives you the extent of relationship between your independent variable and the dependent variable. Let us say in a particular case the value of r squared is 0.85, means what? This implies what? I said that when r squared value is 1, the independent variable is fully explaining the variation of y. When r squared is 0.85, obviously the independent variable is able to explain the variation of y to an extent of 85%. 85% of the variation of the dependent variable is explained by the independent variable chosen for the regression analysis. So, you can get a clear idea of the effectiveness of the set of independent variables that you are using in the regression analysis from this particular coefficient. Clear? Of course, the square root of the coefficient of determination is termed as correlation coefficient. This is one way, or there are other methods also available to calculate correlation coefficient. And a second useful measure of variability of a regression line is the standard error of estimate, which is estimated as SE to be equal to sigma yd squared by n minus k. I am directly giving you the result, proof and other basic information. You please go through the relevant books and try to understand. SE here is square root of sigma yd squared divided by n minus k, standard error of estimate, where the denominator n minus k, denominator of the equation for SE is n minus k. The denominator n minus k is called the number of degrees of freedom associated with the sum of squares sigma yd squared, number of degrees of freedom. This is the explanation for number of degrees of freedom. The number of degrees of freedom may be determined by subtracting from the number of observations n the number of statistics that had to be calculated from the sample to obtain the sum of squares, right. Total observations minus the number of statistics required to get the value of sum of squares, in this particular case yd squared, sigma yd squared. Okay. How many statistics are to be calculated to get sigma yd squared? Sigma yd is nothing but deviation of the observed value of y with respect to the regression line. So you need to get the regression line first. To get the regression line, you need to have at least two statistics, namely x bar and y bar. You need to calculate, then only you will be able to go further with the values of small x and small y to calculate the regression coefficients and then get the equation for the regression line. Okay, that is what is meant by the number of statistics required to estimate the value of sigma yd squared. Okay. For example, for a simple regression equation with one independent variable, the two statistics to be calculated to obtain the sum of squares, or as I said x bar and y bar. So the k value is 1 in this particular case, and then the regression coefficient b is a statistical estimate. Obviously we estimate the value of b because there is no direct equation available to get accurate value of b, and is therefore subjected to error, and it is better to check for the error associated with the regression coefficient by some statistical measure. The standard error is a concept used to convey the magnitude of this error and is estimated from the following expression. This is the standard error associated with the regression coefficient b. SEB is equal to square root of SE squared divided by sigma x square, and of course SE is nothing but the standard error of estimate for the regression as a whole as explained earlier, and sigma x square is the sum of squares of the deviations of x observations about the mean, or in other words it is nothing but x minus x bar whole square summed over all the values. Clear? Now the t-test may be used to determine whether an estimated regression coefficient is significant by forming the following ratio. the value of t can be estimated simply by dividing the regression coefficient by standard error of the regression coefficient, just a statistic divided by the standard error of that particular statistic. Okay, that is how we get the value of t. And with this understanding, let us consider a small numerical example of development of trip production equation involving again only one independent variable, right. The example is this: you have been asked to develop a trip production equation and calculate all the relevant statistics to check the validity of the equation using the following data. This is the data given: average household size 2, 3, 4, 5 and 6, average total trips made by each of the households per day 5, 7, 8, 10, 10. Which is the dependent variable here? The first row values or second row values? Dependent variable. Second row values are dependent variables and first row values are independent variables. Okay. Trip production depends on the household characteristics. Household size is the household characteristics, and the average total trips made by the household per day is the trip production rate, isn't it? Let us try to work out the required statistics first and then go for getting the regression equation. Of course, another information available here is the value of t statistic for 3 degrees of freedom at 5% level of significance is 2.353. This information is required because finally to get the statistical validity of any regression coefficient, we will be comparing the table value of t with the actual calculated value. Here the table value is given as 2.353 at 5% level of significance. Why 5%? Why not 10% or why not 1%? Can be anything, it depends upon our expected level of accuracy. Normally in most statistical experiments 5% level of significance is acceptable. That is how here the 5% comes in. You can aim for 1% level of significance, that means 99% accuracy, okay, that is also acceptable. This is the given data of the dependent variable y values, and the sum of all the y values is 40. We have 5 observations, and the 5 x values are shown here, and sum is 20, and we are ready to get the values of y bar and x bar. Y bar is simply 40 by 5, which is 8, and x bar 20 by 5, 4. Then we can get the values of x minus x bar and y minus y bar, or lowercase x and lowercase y. So y minus y bar, which is small y, is calculated and shown here as minus 3, minus 1, 0, 2 and 2. Similarly, x minus x bar values are calculated as minus 2, minus 1, 0, 1 and 2. Then we need these statistics also for our subsequent calculations. Square of the deviations of the observed values from their respective means, x square is required. So we get the squared values of x as given here, and the sum is 10, and y squared values are also given, the sum becomes 18 just squaring the values already given in the table. And then xy is also required, product of x and y. So we get the values as 6, 1, 0, 2 and 4, and the sum is 13. Now we are ready to calculate the value of b, the regression coefficient, given as sigma xy divided by sigma x squared. The values are already calculated. Sigma xy is 13 and sigma x squared is 10. 13 by 10 is just 1.3, that is the regression coefficient. And we can also calculate the value of the intercept constant a as y bar minus bx bar, because the values are known to us now. So we can get the value of a as 8 minus 1.3 into 4 to be equal to 2.8. Now we know the values of a as well as b, so we can even write the regression equation. This is the regression equation. Ye is equal to 2.8 plus 1.3x, right. So once you have the regression equation, you can get ye values for all the 5 observations. What is the estimate of y based on this regression equation? That is our concern, isn't it, because we want to use this regression equation to estimate the value of y for a similar situation. It is a very general equation. So let us try to get the value of y based on regression, which is ye. So if you substitute the value of x for each observation in the equation, you get the value of ye as 5.4, 6.7, 8.0, 9.3, 10.6 and 40, isn't it, against the observed values of, you just have a comparison. The observed value of y is 5, the corresponding regressed value is 5.4. Observed value of, second observed value of y is 7, the corresponding regressed value is 6.7. Then for 8 it is 8, exactly same value. For 10 it becomes 9.3, for 10 10.6. Of course the sum is same, right. This is how we estimate the value of y. Then deviation yd, because finally we would like to know the exact extent to which x is able to estimate the value of y, isn't it, that is our objective. So we need to have the values of the deviations and then their squared sum. So yd value is this much and yd square you calculate and then sum up, you get sigma yd squared as 1.10, isn't it. Then get the value of ye. Ye is what? Ye minus y bar. Ye values are known, y bar value is just 8. So we find the difference and get the values as minus 2.6, minus 1.3, 0, 1.3 and 2.6. And ye square is our interest. Ye square is simply the square of the previous column values, and we get the sum as 16.90. And then let us get the r squared value as sigma ye squared by sigma y squared, which is equal to 16.9 divided by 18, that is equal to 0.939. And standard error of estimate is equal to square root of yd squared by n minus k, sigma yd squared is 1.1 as we have seen earlier, and value of k, the number of degrees of freedom in this particular case is 2 as I said earlier, because the number of statistics to be calculated are x bar and y bar. So 5 is the value of n, total number of observations. So 5 minus 2 gives you the number of degrees of freedom. So this is equal to 0.6055. What is the inference out of these statistics? Goes R squared. The x is able to explain 93.9% of the variation of the dependent variable y. So it is really an effective variable in this particular case, right. And let us see how to go about using the value of SE and get some inference. And standard deviation is related to the observed value of y, right. That is calculated using the normal formula, again n minus the number of degrees of freedom. In this case the number of statistics required to be calculated to get y squared is only 1. If you know the value of y bar, you get the value of small y and then y squared. There is no need to have 2 statistics. That is how the number of degrees of freedom is 1 more than the case where we calculate the value of SE. Okay. So that is how you need to understand the variation in the number of degrees of freedom. So this becomes 2.12. Will you be able to perceive physically what we really mean by SE and SD? What is standard deviation in general? The scatter, the level of scatter of observed values with respect to the mean, isn't it? That is how we understand standard deviation, right. And the standard error of estimate is nothing but again this scatter of the observations with respect to the regression line instead of the mean line. That is how we just understand YD, deviation of the observations with respect to the regression line, isn't it. If the scatter of the observed points with reference to the regression line is less than the actual scatter of the observations with respect to its own mean, what is the inference? The regression line is relatively more closer to all the points compared to the mean of the observed points, isn't it. So if SE is less than SD, we can say that it is good or bad? Good. Okay. SE in this case is less than SD, hence it is okay. There is another way of looking at the correctness of your regression analysis. Compare SE and SD value. And standard error of estimate of the regression coefficient itself is given by this equation, SE squared by sigma x squared, as I have shown you earlier. So substitute the corresponding values and we get the value to be 0.1915, and then it should be possible for us now to get the t value as the regression coefficient divided by the standard error of estimate of that particular coefficient. So t is nothing but b by SEB, that is equal to 1.3 divided by 0.1915, which is 6.789. Desirably, if the denominator is small, we are going to get a higher value of t. And for the regression coefficient to be significant? Do you expect the denominator to be large or small? Again, standard error is similar to standard deviation, isn't it? It is nothing but statistic divided by standard deviation of that particular statistic or standard error of that particular statistic. The denominator is smaller, the denominator better is the effectiveness of the regression coefficient, isn't it? So that is what we do here. T here is greater than the table value of 2.353 at 5% level of significance for 3 degrees of freedom, isn't it? For estimation of standard error of estimate, we had k value as 2, so number of degrees of freedom is 5 minus 2, only 3 degrees of freedom, right. For that, the expected value of t as per the expectation of 5% level of significance is only 2.353, but our calculated value is much higher, so we can say that the significance is more than 5%, isn't it? Obviously, you can also work out the exact percentage by equating or by looking at the table and finding out the percentage which matches your calculated value, that is also possible. Now the inference is the significance of B is much higher than the 5% level, isn't it? The value is very high, right. And let us have few questions related to the analysis we have done. We have regressed one independent variable against a dependent variable, right. The independent variable was nothing but the number of trips made for any particular purpose, for all purposes. Total number of trips made by a household for all purposes together, okay, and the independent variable is just the household size. Would it be a practical situation? Do we really develop trip reduction model relating trips made for all purposes and the household size? It is not going to help us in practice. In practice, we will be developing regression equations for trips made by households for different purposes. We will have a set of 5-6 trip reduction equations. One trip reduction equation for work trips, another equation for educational trips, third one for shopping trips, fourth for personal business trips, and so on. Why? As I said earlier, the set of independent variables that will influence these categories of trips are going to be different, or even if they are same, their extent of influence of different trip types will be different, right. In case of educational trips, for example, trip reduction for the purpose of education, the likely independent variables are, yes, number of students in the household, definitely that will be one of the variables. Then there could be other causal variables like household vehicle ownership or income, right. Very rarely we just develop trip reduction equation with only one independent variable, at least more than one independent variables are common in any trip reduction equation. If we take trip reduction equation for shopping trips, then household income might be a very important variable, plus could be level of vehicle ownership, isn't it. So that is how we must identify and pick the causal variables to develop trip reduction equation. So this example is not suited for real life situation, This example has been given to you just to understand or demonstrate the analytical principle involved in the regression analysis resulting in a trip reduction equation. This is meaningless as far as practical application is concerned. Okay, we need to understand this point very clearly. Then the values of the variables, we have given some household size as some numbers. I will just quickly go back to the data. Yeah, this is the example. Average household size is 2, 3, 4, 5 and 6 for 5 cases. Are they 5 independent households, or they cannot be independent household because it is clearly stated it is average household size. Average of how many households? How do we take this average? These are zonal averages. We divide the entire urban area into traffic zones. So for trip reduction analysis we deal with zonal average values. So here the average household size means if there are 10,000 households in a traffic zone, it is the average value of all the 10,000 observations, right. And if you look at the other variable, average total trips made per day by that particular household, the numbers given are whole numbers, but when you work out these values in practice you may end up with fractions also. You may end up with trips like 5.25, 7.10 and so on, because you are taking averages, right. But you can work with these fractions even though they are not realistic, and then later on finally you can round off the values. Since these are averages, you have to put up with unrealistic numbers and go ahead with your analysis and finally round off the values to get the appropriate numbers for subsequent analysis. Again these are zonal average values. This needs to be understood very clearly. Right, and this is the case of a single independent variable, and as I said, in reality you may have to deal with more than one independent variable. What happens to the regression equation if you have, let us say, 2 independent variables? I will just show the equation for 2 independent variables case as ye to be equal to a plus b1 x1 plus b2 x2. There are 2 independent variables x1 and x2, and if you look at the equations for calculating the regression coefficients, this is the equation for calculating the value of b1. You can perceive the way the complexity of the calculations increase. It is an exponential growth of involved work in the form of calculation of the values. b1 can be calculated as sigma x2 square into sigma x1y minus sigma x1 x2 into sigma x2y whole divided by sigma x1 squared into sigma x2 squared minus sigma x1 x2 whole square, and b2 can be calculated as sigma x1 squared into sigma x2y minus sigma x1 x2 into sigma x1y whole divided by sigma x1 squared into sigma x2 squared minus sigma x1 x2 whole squared. Of course some of you will be able to memorize these equations and still manage to do regression analysis involving 2 independent variables it is easy to memorize. You can just see the denominator is same in both the cases, denominator is same in both the cases, and if you interchange x1 and x2 for the numerator, you will get the equation from the first equation. Second equation can be obtained from the first equation. You have to write x1 in place of x2, that is it. So it is possible to memorize and go ahead, and you can calculate the intercept constant as y bar minus b1 x1 bar minus b2 x2 bar. What will happen if there are more than 2 independent variables? The equation is going to be highly complex. It may not be manually possible to manage such calculations, and it will be highly time consuming. What to do? Nothing to worry, there are program packages available to do regression analysis. Some of you might know that even your Excel of MS Office has one module for doing regression, simple regression analysis, it is possible, and there are exclusive program packages for doing linear as well as non-linear regression analysis involving any number of independent variables, and give lot of statistical measures related to all the involved variables as well as overall fitness of the regression equation, right. And R square is calculated following the same formula as we did in the case of one independent variable. R squared can be calculated as sigma ye squared by sigma y squared, and standard error of estimate for the regression equation as we did earlier. The only difference is number of degrees of freedom is different here because we involve 2 independent variables, so it becomes 3 sigma yd square divided by n minus 3, and there are 2 regression coefficients. So SEB1, E is not shown here, but you can understand this as standard error of estimate for regression coefficient 1. SB1 is square root of SE square divided by sigma x1 square into 1 minus R12 square, and SB2 is square root of SE square divided by sigma x2 square into 1 minus R12 whole square. What is R12 here? Any idea? R12, it is nothing but a correlation coefficient, where R12 square is a squared multiple correlation between variables 1 and 2. You may recall the formula for simple correlation coefficient. The coefficient of correlation between any 2 variables x and y. Let us not confuse this x and y with our dependent and independent variables. This is just 2 variables x and y. To understand the concept of correlation coefficient, we just calculate Rxy to be equal to sigma xy divided by square root of sigma x squared into sigma y squared. On the same lines we calculate R12 in the previous case, right. X1 and x2 is calculate taking those 2 things as 2 variables. Is that clear? Now the points to be remembered in this lecture are that the regression coefficient is a very important indicator of the effectiveness of the regression analysis. We should not depend only on R squared value. It is better to check for the effectiveness or significance of the involved independent variable. The effectiveness of the independent variable can be checked using t-test for any desired level of significance, right. we can also check for the overall effectiveness of the regression analysis by comparing standard error of estimate of the whole regression process and the standard deviation of the y observations, isn't it? And in practice we may have to deal with more than one independent variable to develop trip production models. So when the number of independent variables increase, the complexity of analysis increases exponentially, and this complexity can be tackled by resorting to the help of the available program packages, and you can do regression analysis involving any number of independent variables and develop trip production models. And finally we need to understand that the dependent and independent variables are zonal average values, they are not specific to any particular household. So we are dealing with zonal average values, treating traffic zone as a trip production unit, and this has to be understood while developing trip production models. With this we will conclude our discussion for today. We will continue with the rest of it in the next class.